Yes, sir, you can start.
Okay, thank you. So, good morning, all the participants. Once again, welcome back to the fourth day of this 1 week FDP. So, I am once again back here to deal with this topic of unsupervised learning. Yesterday, we have seen the topic of supervised learning. Now, we will see how to form groups, inherent groups, or how to form groups within the data with the help of unsupervised learning techniques. Right. So the agenda for today is like this. These are the topics that I am going to cover. The definition of unsupervised learning, the basic concepts in unsupervised learning, then what are the applications relevant to mechanical engineering, then we will see two different clustering algorithms like k-means and hierarchical clustering, and then we will understand what is meant by curse of dimensionality and its connection to clustering. Then how do you handle that curse of dimensionality problem? Uh, the technique that will be used is dimensional reduction, right? And the approach is dimensional reduction, and the technique used here is PCA, right? Followed by uh, good understanding about unsupervised learning for the in terms of what you say anomaly detection. So does always forming groups of data help you to find patterns in the data, or whether the patterns could be sometimes anti-patterns. With the word anti-patterns, the what I mean is the characteristics of normal clusters, right, are one, and the characteristics of this but some x particular group is altogether it is different, right? So these patterns, how do we identify? How can we resolve the issues? We will discuss, right? So fine. So let us start the session. So what is meant by unsupervised learning? So unsupervised learning is a type of machine learning in which we will have only input data and we don't have output labels associated with it. So this is in theory and right, but in practice, in real time, data comes with labels, right? We actually ignore the label information while we need to perform clustering or we need to perform grouping. Clustering is nothing but the process of grouping similar data items, right? So why we are talking about the word clustering when we are talking about unsupervised learning, right? Clustering is a sub process involved in unsupervised learning. So this is one of the one of the techniques in unsupervised learning to form groups in the data from the data, right? So the difference, the basic difference between the supervised learning and unsupervised learning is in supervised learning, the learning actually happened with the help of what you say learned by examples mode. In which mode it has happened? It is learned by examples, which means every example or every instance in the data set contains at input attributes and followed by its label. So based on the label information for a corresponding data instance, it is possible to form groups or categories there. So there is a clear cut information in order to how to form categories or groups because the label is responsible for that. But when it comes to unsupervised learning, there is no concept of label present in the data, right? So we ignore label part from the supervised learning data set, and then we try to form inherent groupings only on the basis of learning by observations mode, right? What is meant by learning by observations? So comparing the examples among each other or in between themselves, right? So first example or first data instance is compared with the second data instance to find similarity between them, right? In terms of attribute by attribute, right? The attribute value of first instance and the attribute value of the second instance is compared. So based on the return, what kind of value you should return, if both are same, you will return 1 or 0. Accordingly, it will generate the similar information or dissimilar information, right? This is the basic notion of identifying similar records in the given data set, right? What if the case when the attributes are holding continuous data, numerical data, right? So if the data is numerical in nature, then how do you find similar records or similar instances, right, in order to form groups? So then we have the concept of proximity, right? The term proximity is used in uh, the process of clustering. So the proximity means the distance, how these 2 points are, with how much distance they are there and how much nearer it is there. The proximity generally talks about nearness of the points, right? So how near the points are, right? If the distance is less, we say they are in highly proximity region. So if the distance is high, the proximity is less, we say, right? So we need to use the term called proximity in understanding the similar records when the attributes are holding continuous data or numerical data. So if you observe in this slide, there is a image showing uh, the grouping of the data, and the groups are formed uh, in the form of both globular and non-globular structures, right? What is a globular structure? So globular structure is a geometrical structure, right, which everyone is able to understand, right? So we have a circular cluster, right, a cluster in the form of circle. We also have other two clusters which does not have a regular shape, right? The shapes are non-globular in nature. So it is possible to form non-globular structures in the while we are trying to identify clusters, right? It is not wrong to form non-globular structures. It is the first important point that one need to clear, right? One need to have clarity, because we generally feel that when we form clusters, if it does not follow any geometrical shape, we generally feel that it is not a cluster, right? But that is not the case. Clusters can be in any can be formed with any global with any shape, right? It does not mean that it should have the globular structure. It can form with any shape, right? Now, so connection between the clustering and unsupervised learning, as I told you earlier, clustering is a subcategory of unsupervised learning. So what we do is, in this task, we group similar data points, right? We group similar data points. So immediately we will come to know how we will group the points. As I told you, proximity measures and similarity measures we will use to group the points, right? But is it that easy to group the points in the absence of label information? Is it that easy to group the points is the most important aspect of aspect while we are doing clustering, right? So unsupervised learning as a broader concept includes so many other tasks beyond clustering. All but actually all of them are focusing on only one point: how to group the how to group the patterns, right? Patterns are nothing but similar records here, right? So now if you observe, I would like to ask you people, uh, how many of you people will come up with how many number of clusters based on the top left corner representation of the points, right? So you don't see the remaining ways of generated clusters, but you please tell me, based on your intuition in the chat box, how many clusters you can form, how many groups you can form, right? Please tell in the chat box. participants, I think you people are with me. I asked you to tell me how many groups of points are there, right? So one participant has told there is only one group. Other participants are also responding like 3 plus 3, 4, 7, 4, right? I am now able to see a good number of responses here. Now, yes, accordingly, for everyone, you have your own intuition of grouping the points, right? So the basic intuition lies here is the proximity among the points, right? So how near the points are based on the visual intuition that you are grouping the points, right? So some people are coming up with the values of 7, some are saying 6, and some are saying 3, and some one participant has said it is 1, and so on, right? So yes, so now with this particular visual intuition, it is very much clear for all of us that the number of clusters forming number of clusters is itself is confusing, right? So it is ambiguous. The notion of a cluster can be ambiguous, right? Coming up with the right definition of proximity measure or similarity measure uh, is an important task here in the in that process of clustering, right? So what is the optimum one? Any conditions? Yes, statistically we can identify how many clusters we can form, right? So until and unless we don't approach the formalism of from statistics, uh, it is bit what you say, it is bit tough to form, to say that these many number of clusters are there in the data, right? That is the first important point. And second important point is, when before saying this second important point, did I answer your question, sir? So please respond in the chat box if I have had answered your question, right? So
Yes,
then,
sir.
yeah, okay,
Yes, yes.
thank you. And the second point is, now in by when you are using the statistical formalism to form, to say, to come up with the fixed number of clusters, so then it is okay. But as you are considering the label data, the label data has some number of groups. Please try to understand. So if I take the example of iris data set, which is a flower data set, right? It contains 150 records in the data, right? 150 rows in the data. We have 4 attributes in the data set. And the interesting thing in this data set is the first 50 records in the data are corresponding to one particular type of flower. The next 50 records deal with another type of flower. And the third 50 records deal with the third type of iris flower, right? So here, the groupings are very much easy. Our categories are very much clear in the data set, right? So now, as I have removed the label information from the data for the sake of performing clustering, now is it possible to tell blindly that I will have only 3 groups of flowers? Yes. Can anybody respond to this question? Can I say that how many number of categories are there? Only those many number of clusters is possible, especially when the attributes are holding continuous data or numerical data. Yes. So I am seeing the answers. One participant said it is no, and a few other participants are saying it is yes. But the answer is actually no, right? Only one participant has given the answer, correct answer as such, but I don't want to discourage anyone saying that this is correct and this is wrong. Technically speaking, the answer actually is no, right? Which means, if I will take the same example here, like Irish data set, if I consider the 49th record and 50th record and 51st record and 52nd record, right? The 49th and 50th record belongs to first category of flowers. 51st and 52nd record belongs to second category of flowers, right? Now, these four flowers, if you observe carefully in the data set, these four flowers information with respect to the attribute values, right? So there will be certain, what you said, dependencies, right? The 50th record, 50th instance of the flower might be actually falling into the uh, second group of flowers because the value is matching with the second flower range for that attribute. In the same lines, if there is a 51st record for a particular attribute, it might be matching with the 50th attribute uh, based on the value, attribute value. So here, because of this, what happens? Certain records actually, they are actually lying on the border, whether this record should belong to first group of records or it should belong to the second group of records. So uh, this will actually be clarified when there is a label for the record. But strict as we are dealing with clustering, and we are ignoring the information of label, so it is not possible to say that we will have only these many number of clusters. Fixed number of clusters can be formed is not possible to say directly, right? That should be only decided with the help of a statistical measure, right? So we approach statistics and we take the support of statistics. Only then it is possible to come up with the right number of clusters. Yes, I'm changing the slide just to make you understand the concept. I am here in this slide, right? Fine. So as you have understood, the notion of clustering itself is ambiguous. So how to deal with that clusters, we will come to know in few within few minutes, right? But what is meant by good clustering? So let us say here, if you see in this slide, we have three different groups of with three different clusters, right? So if you are taking the distance between 2 points which are belonging to two different clusters, right? The notion of good clusters in terms of this distance is intercluster distance should be maximum, right? The distance between these 2 points should be high, right? Which actually says these 2 points belong to two different clusters. If the distance is more, it means these points are not similar, right? These points are not similar. When it comes to the distance between the points inside the cluster, the distance between the points must be minimum. This is the standard notion that we generally follow to say whether the cluster is a good cluster or a bad cluster. Any doubts here? Right? So based on this particular representation, or based on this particular notation, we can come to a conclusion, initial conclusion, that these clusters are good clusters and these clusters are not that good clusters, right? And not only this particular this particular condition is useful to say that these are good clusters and these are bad clusters, but also based on the type of the algorithm that we use for the sake of clustering, how the initial conditions are used, what are the initial conditions that the algorithm is saying, how to deal with that algorithm to form clusters also affects the representation of good clusters. right? So we will see how the initial conditions of the clustering algorithm affects the quality of the clusters with the help of k-means algorithm, that we will now see within a few minutes, right? So now this is the most important slide, because uh, we need to better understand about the characteristics of the data, because we are only providing input data for the clustering algorithm and we are not specifying any label to that. So that's why we need to understand clearly about the data, right? So now what is the first characteristic? The first characteristic is type of proximity or density measure, right? So which particular proximity measure is to be utilized, or density measure is to be utilized? Because when you plot the data, right, how if you I will simply go to that particular slide where you see the plotting of the data. Let us say you see this uh, data plot, right? How the points are actually plotted, how they are located, right, in this two-dimensional region, right? So you see there are few points that are closely related, they are populated, closely associated, right? So this is with respect to these 4 points, this is a dense region, and when it comes to this particular region, these points are densely populated, right? And if you see in some situations, the density is more, the density of the points are more, right? So you see in real time the data generally looks like this, right? Identifying groups in this kind of data is a challenge, right? The clusters, how do you find clusters from these points is a challenge, and this challenge is actually high, because just by looking at the data with our eyes, it is not possible to group, because there are no inherent groupings in terms of space, right? The points are not well separated. Please try to understand. Here, the data points are not well separated. So when the data points are present in this fashion, and of course, there are many other real world data sets available in which the points are densely populated, more densely populated than this. So in that situation, the type of clustering algorithm will actually vary to form clusters, right? From based on the density of the points, right? So like that, we also deal with different types of clustering algorithms for the different types of data, right? So the first point is in this characteristics, the type of proximity or density measure which you select will actually play a important role for in while doing clustering. The second thing is the sparseness in the data. The sparseness, what is meant by sparse data? Sparse data with respect to a particular attribute is the number of non-zero values present in the, what you said, in that column, right? Number of non-zero values present in that column, and and that number is usually very less, usually very less, right? So and what we generally do in order to fill that particular column, right, fill that particular column with by filling all the cells, what we do is wherever the non-zero values are there, we we map them to one. Wherever cells are empty, wherever cells are empty, we will fill them with zeros. So in that case, we are only left with two values, zeros and ones. So when such kind of data is available, how the clustering algorithm handles that particular attribute for the sake of grouping the points. That is the most important what is a challenge for a particular clustering algorithm, right? Not all clustering algorithms will deal with the sparseness of the data. Only few algorithms are above will take the responsibility to deal with that sparseness, right? And the third characteristic that one need to keep in the mind is the type of the attribute, right? The type of the attribute is crucial, as I told you in the earlier discussion, earlier slides itself, right? If the attribute is holding strings, let us say the color of the eye is the attribute. So the color of the eye can take so many number of values, right? like it could be red, black, brown, green, blue, and so on. So if the color of the eye for in the two instances, data instances are same, then what is the similarity formula that you specify? What is the return value for that, right? So how do you say the two color values are same? If both the strings are same, right, then what you say that these two values are same, right? So this is specific to a particular attribute, right? This is with respect to the string, and the type of the attribute, the values that are taken by the attribute are discrete in nature. The color of the eye is discrete, right? So many different colors are there, right? When it comes to continuous data, if the attribute is a continuous data or interval attribute or a ratio attribute, then how do you formulate the notion of similarity at that point of time, right? So we generally plot such points in the coordinate system, in the two-dimensional coordinate system, and we come up with what is called as distance measures. We come up with the distance measures like Euclidean distance, Minkowski distance, right? So we use those distance measures, and we say that these two particular instances are this much similar based on the obtained distance, right? So we quantify the distance with the help of those measures, distance measures, right? And now we have the type of data. So type of data are could be, it could be ranging from numbers to text to different types of strings, variety of data, like what you say, it could be like weather data, right? It could be like a sensor data, in anything, right? Any type, any data, right? So based on the type of data that you have, you should define what is the similarity measure, right? So you can also deal with the auto correlation with the concept when you're dealing with the type of data, right? Which says how the attribute values are highly similar in nature. So right, so then the next characteristic of the data is dimensionality. Dimensionality uh, means the number of attributes present in the data, right? So if the number of attributes are many, right, as we have seen in the EDA process, we have seen 52 sensors as attributes, right? So that kind of data is high dimensional data, right? So if the attributes are very less, like two or three in the data set, that is a low dimensional data, right? Altogether, the dimensionality is nothing but the number of attributes present in the data set. So if the attributes are high, then the computational complexity of for carrying out the clusters will be high. So in that case, we need to deal with the problem of curse of dimensionality, and we need to come up with a solution to handle that dimensionality issues, right? So then in that case, what happens is when there is a problem of high dimensions, then the notion of similarity, the notion of proximity and similarity is meaningless, right? It is not correct to say that these points are similar in nature, because dealing with that many number of attribute data is is computationally complex with respect to usage of that particular distance measures or proximity measures. So instead of working with that particular proximity measures on huge number of attributes, why can't we reduce that attributes, or why can't we introduce a notion of what you say variability with by reducing the attributes to a new form, and saying that this new form is responsible to reconstruct the original data, right? So that is what we will try to understand when we deal with the concept of PCA today, right? Then we also deal with the we also should identify the outliers present in the data, right? So outliers and noise, right, both are different, please try to understand. So noise is something that a human can introduce, right? That not only human can introduce the noise, but also while measurements, noise can also come into the recordings, right? So not only this noise information is present in the data, but also outliers are those set of points whose characteristics or properties are different from remaining points. So obviously you should deal with this now noise and outliers. Data will possess real-time data will possess noise and outliers, right? So then we are dealing with also the type of distribution. So how the data is actually distributed, what is the basic assumption underlying the data. So whether the data uh, follows like Gaussian distribution, whether the data is binomial distribution, following binomial distribution or not, and so on. Accordingly, we need to formulate the clustering mechanism, and we should come up with the clusters, right? So we should keep all these things in the mind, and wherever these characteristics are identified, accordingly we need to come up with the distance measures, right? So there are major these are the major clustering approaches. We have partitioning algorithms, hierarchical algorithms, we have density based algorithms, grid based algorithms, and model based algorithms, right? So we in this today's theory, in this today's lecture, morning lecture, we are going to see one algorithm from partitioning algorithms and one algorithm from hierarchy algorithms, right? So if you see here, what are partitioning algorithms? The partitioning algorithms are those algorithms which generate partitions in the data, which create partitions in the given data, and these partitions actually follow right, a similar pattern. The points in that partition are said to be similar, right? Now data points in that partition are said to be similar, right? On what basis we are saying that the points in that partition are similar? So we deal with a what is a summary statistic, like descriptive statistic, like mean, like medoid or median. So you can use that particular descriptive statistic, and we compare uh, each and every point in that particular region with that particular what you say mean or medoid, and we'll come up with the notion of similarity or grouping, right? Then we once we understand how partitioning algorithms are used for forming clusters, then we will see uh, the hierarchy algorithm, how hierarchical decomposition of the data helps you to form the clusters, right? So are we what you say dividing the data, are we combining the data? There are two ways to form clusters and two ways to understand to in forming the clusters when we deal with hierarchy algorithms. But in our today's discussion, we only restrict ourselves to deal with how agglomerative hierarchical clustering or hierarchical agglomerative clustering, HAC to be specific, is used to form clusters in the data, right? So uh, beyond this, we also have density based clusters. So density based clusters deal with the concept of density, what is form of the data. So when you plot the data, you will see the data showing in the dense form, right? Right. Then how do you deal with such kind of data to form clusters? We is the approach, right? The next is grid-based approach. In grid-based approach, what we do is we divide the data into multiple levels, right? So the best example that I can quote for grid-based clustering is your Google Maps, right? So in Google Maps, if you enter into the Google Maps, what happens is your your map is actually divided into multiple what you say grids, right? And these multiple grids hold different different pieces of information. And the interesting point here is when you zoom into the map, what is actually happening? You are into a newer level, right? You are in the newer level, and in that newer level, what you will see, the specific data, the specific location that you would like to identify, right? When you zoom inside, you are entering into the what you say, lower levels of the data, representation of the data on the map, and you will see a specific information. When you zoom out, what happens is you are coming outside and you are coming on upward, right? When you are moving up, what happens is you are coming away, getting away from the specifics of the data on the map, and you are reaching to the generic information that the map is actually providing to you, right? So this is grid based clustering of the data, right? So there, how the clusters are formed, that is the most important thing when we see grid based clustering. If time permits, if then we will see some demos with respect to density based, grid based techniques, right? Then also we have model based clustering algorithms, where we deal with the mathematical form for the for making clusters, right? So we limit ourselves to the first two in this discussion, right? So then, so what are the various applications relevant to this mechanical engineering? So the quality control in manufacturing, component similarity analysis in product design, right? Machine condition monitoring and fault detection, and robotics automation, vibration analysis, energy management, material science, right? These are the various applications relevant to mechanical engineering in order to perform clustering, right? Fine. Now, so we now quickly enter into the first algorithm, that is k-means algorithm, k-means clustering. The This is a partitioning algorithm which takes into consideration the notion of means, right? The notion of means. Mean is also called as centroid here, right? So we are dealing with the word called centroid. We consider the centroid information to group the points, right? So now how the algorithm proceeds. If you see this, the algorithm works in this way. First, what happens, given a set of points, what we are doing, we are selecting k points as the initial centroids, right? The algorithm starts like this. It is saying you should select k points as the initial centroids. K, the value of k is not fixed. Please try to understand, right? You can have your own value of k based on the size of the data, right? So now, once you specify k points as initial centroids, there is a repeated there are repeated steps to follow, right, until the centroid doesn't change, right? So what do you mean by the centroids doesn't change? It means you are forming final clusters, right? You are forming final clusters, right? So in order to say that these are the final clusters, so what are the steps that we need to repeatedly carry out? The first step is you form k clusters by assigning all points to the closest centroid. So how do you do that, right? So when you have k initial centroids, it is possible to form k groups. So each group contains that particular centroid, right? So first group contains first centroid, second group contains second centroid, and so on. Now, while forming clusters, we should form the clusters by defining a similarity measure or distance measure, right? So you select a particular distance measure like Euclidean distance, and what you do is you take that centroid point and the point present in that group and find out the distance, right? So like this, how many points are there in that particular group, you derive the distances with respect to all the points by using that centroid. Now what you do is you identify that particular point which is less, whose distance is less with the centroid, right? And assign that point to a particular cluster, to a particular cluster. So we will see how to do that right, with a simple example, right? And once you assign the point to the cluster, right, to which cluster this point is near, once you assign that point to the cluster, you should recompute the centroid of each cluster, because as the points have been shifted from cluster X to cluster Y because of third step, right? You must understand that the centroid will now change, right? The centroid will now change. The centroid should get modified, right? So that modification is done with the help of calculating the centroid, right? So once you calculate the centroid or mean, automatically that particular cluster is now uh, associated with a new centroid, right? And these two steps will be repeated continuously until the centroid doesn't change. How do you find the centroids are not changing? You will find when the centroids in the current iteration for those clusters and the centroids in the previous iteration, right, should not be different, right, should be same, right? If that is the case, you will terminate this algorithm and say these are the final clusters, right? Any doubts with respect to this? So now I will see the chat window if there are any doubts are there. Okay. Now, the thing is, how do we perform this? That is the important point. So now we will see the mathematical what do you say approach with the help of a example data, right? So what I do is I will share this document with you, or in the screen, right? 1 minute, I will share this screen now. K means example. Right now, once again, I will share the screen. Right. So are you able to see the screen document? I think you people are able to see this document. Fine. Now, so you see, this is the data available. So these are the attributes in the data set: the curvature, the texture, and the blood consumption, and the tumor type, right? So we need to group tumors here. We need to group tumors based on the available attributes, right? And as I told you, when you're performing clustering, we will ignore this class label information. We don't consider this. So that's why we are hiding this class label data, right? The only thing that we have is these three attributes information, right? Now, with this data, what we need to do is we need to form clusters or groups, right? So how the groups are formed, right? So to do that, what we are doing is we are considering the algorithm, k-means algorithm, and we are finally forming the clusters, right? So now, to be more specific, we have these points. We have 8 points here, A1 through A8. And by applying the k-means algorithm, what is the first step in k-means algorithm? Choose initial centroids, right? So randomly, we have chosen k initial centroids. What is the value of k in this example? 3, right? We have taken 3 initial centroids, and that too random in nature, right? So 2 comma 10, 5 comma 8, and 1 comma 2, right, are the initial centroids. Now what we are doing is we are calculating the distance between each and every point, right, to make to fall that point in a particular cluster, right, to fall that point in a particular cluster. Now what we are doing, what is the distance between this point and the first cluster mean? It is 0, right? What formula we are using? We are using this Euclidean distance, right? We are using this Euclidean distance and to find out the value, right? So we are taking the distance between this point and the cluster mean, it is 0, right? And from here to this second cluster mean, it has some value. A1 to the third cluster mean, it also has some value. But if you see all these three values, right, 0, 5 and 9, among all these three values, for which particular cluster the distance is less, which for which particular cluster mean the point is nearer, it is the
It is first one.
first one.
Means
So
mean.
it is first one, correct? So what we are doing is we are saying that this point should belong to first cluster. So this is first partition, this is second partition, and this is third partition, right? So now the first point will now belong to first cluster. In the same lines, for all the points, what we are doing is we are calculating the distance, and we are assigning that point to that particular partition whose distance is less, right? So now the populated table looks somewhat like this. So this is the populated table, right? So this like this, these points are now assigned to three different partitions, right? Here we are saying those partitions are clusters, right? Now how many points are there in first cluster? From this list, how many points are there in first cluster? So 1 point, sorry, 1 point is there in the first cluster, that is 2 comma 10. So this is the point in the first cluster. So how many points are there in second cluster? 1, 2, 3, 4 and 5. So these 5 points are what is it, grouped as in the second cluster, right? And how many points are there in third partition or third cluster? 2 points, right? So these two are 2 points. So these 2 points, they form another cluster, right? So now what we are doing is we are visualizing these points and we are making as what is a groups in this fashion on the coordinate axis, right? So you see on the coordinate system, we are plotting the points and we are forming the clusters, right? We are forming the clusters and we are also identifying the initial centroids. So how we are identifying the initial centroids? With the help of some notation or representation. So here we are using color coding to differentiate the initial centroids with the other points. So we are using red colors to say that these are the initial centroids, right? Now, so now after forming the clusters, as this is the first step, first iteration, there is no point in saying that actually the point A8 is belonging to third cluster, let us say, or second cluster. You should go to first cluster because the distance is less, right? For example, I'm saying. So this is only understood when we update the mean value, centroid value, right? So for that, what we are doing is we are updating the centroids, right? How we are updating the centroids? We know the formula, right? What is the formula for updating the centroids? So based on the number of points in the cluster, we are defining the centroid formula, right? So A2 and A7, what are A2 and A7, right? For cluster 1, we have only 1 point, that is 2 comma 10. The cluster centroid remains same. For second cluster, we have these many number of points. So the centroid formula is all the x values, all the x coordinates, sum of all the x coordinates by the number of coordinates, comma all the y coordinates, sum of all the y coordinates by the number of coordinates, right? Number of y coordinates will give me the new centroid, right? If you see, so here the value, here the computation of the cluster centroid is present in this fashion. So the updated cluster centroid is now 6 comma 6. Earlier, what is the cluster value, cluster centroid value? 5 comma 8. Earlier it is 5 comma 8. Now it is 6 comma 6, right? Now, because the cluster centroid has got updated, automatically some points will now move inside the cluster, or some points will move away from the cluster also, right? Altogether, when the points move away from the current cluster, that should be either entering into a new cluster, or it should not be entering into any cluster. Only two things we have, right? If the point is entering into new cluster, that means there is a the initial centroids that we have considered are some has some meaning. If the initial centroids that we have considered is posing certain problems in such a way that the movement of the points from one cluster is not leading to a new cluster, or altogether it is keeping away from itself, then the considered initial centroids are problematic in nature, right? So fine. So see, the in the third cluster, how do we update the centroids? So this is the way we know the number of points in third cluster are only 2. So 2 plus 1 by 2, 5 plus 2 by 2. So this is the updated centroid, right? Now, what are the points in the new cluster? So in the new clusters are A1. The first cluster contains only one point A1. Second cluster contains these points, and third cluster contains these points with the updated centroids. Now, with the updated centroids, you see the representation, right? So now what you are doing? You are now once again calculating the distance between every point in that particular partition to this centroid, and finalizing to which partition that point belongs to, and forming new groups, right? And forming new groups, right? You see, here new groups have been formed, right? Earlier, in this second iteration, right, the points have got adjusted, right? Earlier in first group or first cluster, only A1 was present. Now the point 8 A8 has been entered into A1 cluster. So earlier, as I told you, A8 is nearer to A1. Obviously the distance measure will take this point away from this cluster, and make that point enter into the first cluster, right? That is what has actually happened here, right? Now, if you see carefully, A4 and A8 are very much nearer. Obviously, it is understood that in the next iteration, this point also moves to the nearer partition, that is first cluster. So as you see in the third iteration, the point has moved to the first cluster, right? Now, if you see, these points are very much nearer, and these points are very much nearer, and this point and this point are farther. The point present in this cluster and the point present in this cluster are highly dissimilar, in the sense that the distance between these 2 points is high, but the distance between these 2 points is less, right? Please understand that this representation of these clusters is not to the scale, not to the standard scale, right? I am not dealing on the graph, right? I am only showing on a simple square matrix kind of thing, and showing you how the points are actually getting plotted. And these iterations will come to an end until the centroids will not change from previous iteration and the current iteration. So any doubts with respect to this K-means algorithm? Any doubts? Please let me know.
No, sir. Continue.
Fine. So thank you. So now when this algorithm is this good in partitioning the points, now what are the challenges that the people face while using this clustering algorithm, right? So if we blindly consider, right, of course we are selecting the initial centroids in the random fashion only, because the algorithm is saying that select in random the initial centroids. It could be based on your k value, right? But doing that way every time will not lead to good clusters. That is the most important thing, right? Because initial centroids, if you consider initial centroids are poor, then automatically what happens is your k value will be lost. The number of clusters will be lost, right? Why? In the sense, altogether, some set of points will form a new group, right? Which is not ideal, because you have started with one k value. Now you are seeing altogether a new k value, or altogether the set of points, what is a spread in random,
Sir,
right? Yes,
see this method, iterative nature. What is the condition that the clustering is completed?
that's what the
Yes.
when can I say the clusters are formed, or what you say final? It is based on the means that you observe. In the current iteration, what are the cluster means or cluster centroids? And in the previous iteration, what are the cluster centroids? Compare the cluster centroids of previous iteration and the current iteration. If both the cluster centroids are same, then the algorithm will get terminated. That is the condition that we apply while in order to
Okay.
terminate the algorithm. Understood, sir?
Yes, sir. Yes, sir. Okay. Okay.
Okay, thank you. Now, so what are the problems with this particular k-means algorithm? So for that, uh, the thing is, as I told you, the initial centroids, choosing initial centroids itself is crucial to form good clusters, right? So, and also, not only initial centroids will affect the uh, forming of good clusters, but also the what you say, the statistical value, SSC. Now SSC stands for sum of square error, right? Sum of square error. Uh, so the sum of square error is actually a statistical formula which calculates the square errors inside the particular cluster between the points. Initially, it forms square errors in the within the cluster. If all the square errors for all the clusters have formed, what happens is finally it sums all the square errors of all the clusters to form sum of square errors, right? We see the formula of SSC now. So in the presentation, we will see now. So I think you people are able to see this presentation slide, or should I once again share the slide?
Sir, reshare, sir.
Right, once again, I am sharing the slide. Now I hope the slide is visible. Fine.
Yes, sir. Visible, sir.
Okay, so
Sir, in the presentation mode, sir.
fine. So these are the steps that we have followed in understanding that numerical example in for forming K clusters, right? So now you see two different k-means clusterings. So here use these are the original points. Actually, in real world, this is not the way the points will actually get located, right? The points are distributed in a either in a uniform way or in a dense way, right? Like this, the groupings of the points are only present if the data is uh, tuned as per the requirements, right? So this is not the case in the real world, right? Now, if you want to form three clusters with k-means, so you specify the value of k to be 3, and the initial you are able to see three clusters here, right? So this, when you want three clusters, and if you are seeing the three clusters after k-means algorithm, then it is optimal clustering, because the initial centroids are also supporting to form optimal clusters, right? Correct number of clusters. But this is a suboptimal way of doing clusters, forming clusters, because what happened, you asked for three clusters, but it has written four clusters, right? This is not correct, right? This is because one of the major reasons is the selection of initial centroids, right? So see here. So now I will show you that time. Where is that? I think, okay, fine. This is due to poor selection of initial centroids. This problem will occur, right? So please let me know what could have happened here uh, to have four clusters, to form four clusters. We have started with three. Why the K-means algorithm is showing us four? Can anybody tell me what is the reason?
Selection of centroid might have been leftmost, I think, leftmost for the blue color. That's why.
The selection of centroid is
I
specific
mean,
to the left grouping.
yeah, far away from the particular cluster.
That is one point. What is the other point, sir? Most important point. The other point is the distance measure. Is that right?
Yeah, yeah.
So the considered distance measure also, what you say, also has a certain effect in grouping the points, right? Right, and the cluster and the centroid is actually, if you see, the centroid now has got divided into two different centroids. So because of this, you started with three and end up with the four clusters. So this is a suboptimal way of forming clusters with k-means. So how do we overcome is another part of discussion, right? So what are the ways to handle this situation? What are the techniques to mitigate this are also present. But for now, I am what to say, I limit myself in discussing or concentrating on SSC, right? So how do we evaluate the generated clusters, k-means clusters? So as I told you, you form what is called as SSE, sum of squared error. So sum of squared error has two summation symbols, you see, right? Two sigma values, right? So the internal sum, internal sigma is all about the distance between the cluster center and the point within the cluster, right? So X belongs to Ci. Please, this representation is very important, right? In a cluster, what you are doing is you are finding the distance between the cluster mean or cluster centroid and the point, which you have already done, right? Which you have already done, right? Which is part of the k-means task, right? Which you are doing, and after doing that, what you are doing, so the all the distances are what you are summing up, right? You are summing up the squared distances. Once you find out the distance, you are squaring those distances and you are summing up all those distances in a single cluster. And you must do, right, this for all the individual clusters, right? You must do for all the individual clusters. Here, let us say we have the value of k to be 3. So for each cluster, you are doing the internal sum. So once you do for each cluster the internal sum, for every cluster, when you do this, you will have a specific sum value, specific sum value for each cluster. And the outer sum symbol is what it is doing is it is adding up these sum values across all the clusters to form the entire SSC, of the clustering process, right? This is for the individual SSC, entire individual cluster SSC, and this outer sum is for the entire clustering process. These two things form what is called as SSC for the clustering process. And what we need to understand here is, if the clusters are seen to be good clusters, when can I say that a cluster is a good cluster? When the SSC value is less. Please try to understand. When sum to squared error value is less, then we can say that the obtained clusters are said to be good, right? So you see, given two clusters, we can choose the one with the smallest error. That is what I said. Any cluster whose SSC is minimum, or the entire SSC is minimum, right? So we can choose that cluster. The one easy way to reduce SSC is to increase the value of K, right? But it has its own problems, right? So a good cluster with a smaller K can have lower SSC than a poor cluster with higher K, right? So this is a point that one need to keep in mind, right? So when you increase the value of K, the SSC value actually comes down. So this kind of uh, seeing or observing the value of SSC coming down when you increase the value of K is quite is possible with Veka tool. Veka is a data mining tool which is used across the globe for doing machine learning as well as data mining tasks, right? So when you use that Veka tool, there is a option called SSC. When you select that SSC option, so that SSE will it will generate the value of SSC when you modify every time the value of K. And what you can do is you open an Excel sheet and form two columns. The first column is the value of K. The second value is the column of SSC. Right now, what you do is you select all those points. How many K values you would like to see for those many K values? You generate SSCs and select those two columns and plot a line plot. So that line plot should show something like this. It should show something like this. And this plot, the name of this plot is nothing but elbow method for finding optimal value of K, right? So you started with a wild guess of having K number of clusters. Does the K number of clusters are actually the same number of clusters which are to be retained, or do we need to change the number of clusters? That is obtained with the help of this elbow method. Now, what this elbow method says, when you plot this line plot, on x-axis you have the number of clusters, on y-axis you have SSC. The other name for SSE is inertia, right? So now when you plot this, and at one particular value of K, suddenly this particular line plot bends, right? This particular line plot bends. So you should identify at which particular value of K the line bends drastically, right? In this particular plot, we it is very challenging to identify the value of K. And uh, for as we have seen three clusters beside, right? So we treat that value of K to be 3 here. We treat the value of K to be 3, and we understand that at the value of at the value of K equal to 3, the elbow has said to be bent, right? The elbow has said to be bent, right? So for some situations, it will be very clear at a particular value of K, the line plot bends enormously, right? But for some situations like this, it is quite challenging to identify at which particular value of K the line plot bends, right? So this is also visible with respect to corresponding SSE value for the corresponding K value in the Excel sheet that you have, right? So you will observe, you can observe there from a particular K value, the SSC drops enormously. SSE value drops enormously. So that particular at that particular point, you can finalize that these particular data set will have these many number of clusters, should have these many number of clusters. Any doubts here? Right? Fine. Now here we are taking the mechanical engineering scenario. 1 minute. We are taking this mechanical engineering scenario. The scenario is quality control in manufacturing, and here we have data points specific to attributes. The attributes we will see, but here the points that the way the points got plotted in this particular coordinate system, right? uh, Actually, the concentration of any particular what you say machine learning engineer will be on how the data points are what you say settled, right? So we have two features. We have considered two feature data here, and we are plotting the points, right? And now we have identified at the value of k equal to 3, the elbow has been bent, right, enormously, and we used the technique of PCA. Of course, no need to use PCA here in order to find to form clusters. You when you set k value equal to 3, you apply that value of k equal to 3 here to form clusters. But here why PCA is used, why dimensionality reduction is done on the data? If you have seen this arrangement of the data, this calls for, right, high dimensional data, right? High dimensional data, in the sense we are not dealing with the number of attributes per se in this discussion. We are dealing with the number of points, right? So when you have these many number of records, right, in order to correctly identify the groups, you can reduce the number of dimensions, right? So you have used PCA here to show up the number of clusters, but okay, fine, no need to use PCA. But as you have found three clusters, the only thing that we need to have is color coding, right? If you have one color for identifying one set of groups and a separate color for identifying other set of groups, then it is easy to identify the groups or clusters, right? So so any doubts with respect to this? K-means clustering. So I hope why three clusters? That's what I'm saying. In this particular visualization, we have identified that at the value of k equal to 3, this particular curve has been bent, right? But it is not clearly visible. That's what I'm trying to say. For not all data sets will show you clear bent in the curve, right? You should carefully check where the bent has actually occurred in the line plot. This is also known as elbow bent method. So where the elbow has bent correctly, and that particular point for that particular value of k, you consider it as the final value of k and plot the clusters. Okay, now fine. So now we go to the second algorithm, that is hierarchical clustering. So in this hierarchical clustering, there are different types of grouping mechanisms, clustering mechanisms in hierarchical clustering. So in hierarchy, we know the word hierarchy. What is meant by hierarchy? Right? What is meant by hierarchy? Levels, right? Hierarchy means levels. So we have different levels to form groups, right? It is possible to form groups by grouping the points at different levels and moving up by merging those individual clusters to form a new cluster altogether, right? So if you see this, so there are four groups here: fish group, reptile group, amphibian group, and mammal group, right? So at this level we have four groups, and these four groups, when we move up in the hierarchy and when we move one level up, these four groups are grouped as one group, and we said that this is a vertebrate group, right? And now in the same lines here, we have three groups here: worm, insect, and crustacean. And we are grouping these three. And when we are grouping these three and moving up in the hierarchy, we have only one group saying that it is invertebrate. The combination of vertebrate and invertebrate form what is called as animal group, right? So that means every we belong to the higher group called animals, right? So mammals are from animals, we can actually infer this, right? We can actually infer this from this particular taxonomy, right? So this is the hierarchy, and this is technique. This is the other name given to this particular hierarchical taxonomy, the name called dendrogram, right? So we form what is called as dendrogram with the help of hierarchical clustering, right? So how we do hierarchical clustering, we will uh, will come to know. This dendrogram can be formed by recursive application of k-means algorithm, right? So by applying k-means algorithm recursively, as you are forming partitions, right? These partitions over a period of time, they form what you say inherent groups, right? The inherent hierarchies. So these hierarchies can be grouped together, right, to form a new hierarchy at the upper level, right? Now, so how the dendrogram looks like? This is the way the dendrogram looks like. So what you are doing, every time you are combining individual clusters, initially we start each and every point belong to a individual cluster in the real time, and slowly what we do is, based on certain distance or proximity measures, we merge the individual clusters to form a new cluster, right? This is a new cluster, and this new cluster, once again, it is merged with the next point to form a new cluster, right? And like this, finally we end up having a single cluster in which all the points are present. This is one way of dealing with the clusters, right? This is a single clustering technique, which says all the points finally belong to a single cluster. Any doubts here? So there is another way. In this form of clustering is known as agglomerative clustering. You are merging the points to form a single cluster, right? The other way is the reverse, where we start assuming that all the points belong to a same cluster, and we hierarchically divide those points, right? And finally what we say is each point belong to each cluster. So this is bottom up approach. Agglomerative clustering is a bottom up approach, and divisive approach is a top down approach in forming the clusters. Okay, now in our discussion, we talk about bottom-up approach of forming clusters, right? And there are different ways to form bottom-up clusters, dendrograms using bottom-up approach, and in which one such approach is simple clustering, and we will see first the various list of clusters, right? So now, so this is the way hierarchical agglomerative clustering happens. Starts with each point as a single cluster and repeatedly merges those points based on certain criteria of closeness to finally form a single cluster, right? So this this merging of these points based on some criteria of closeness forms what is called as a hierarchy, right? Or binary tree, because every time you are only combining 2 points at a time, right, to form a group, right? Now, so what are the various ways to form hierarchical agglomerative clusters? The first one is single link clusters, single link way of clustering. Second is complete link way of clustering. Third is centroid way of clustering. And fourth is average link way of clustering. So in today's discussion, we limit ourselves with single link clustering. And this technique is very important, right? Because what we are doing is we are what you say finding the minimum values every time. Why we are talking with minimum value? Why can't we consider maximum value? We'll come to know when we talk about single link clustering, right? So single link agglomerative clustering. Now, in order to find out the similarity between two clusters, why we are finding similarity between two clusters? As I told you, in agglomerative clustering, we initially assume that all the points are actually individual clusters. So in order to merge those individual clusters, we need to form a similarity measure. So that similarity measure is defined in this fashion for single link clustering. What is the similarity measure? Similarity of the points x comma y of belonging to two different clusters, and that similarity you are maximizing, right? So what do you mean by maximum similarity? What do you mean by maximum similarity between two different points belonging to two different clusters, right? Two different points belonging to different clusters, right? It means what? You see the diagram, you will understand. So if you see this, the point, this is, let us say, the point X in this cluster, and this is, let us say, the point Y in this cluster, right? You are saying that the distance between these 2 points should be minimum, right? You said maximum, right? You will have immediately, we will have a doubt. When will you say the clusters are good clusters? Intercluster similarity should be high, right? Intercluster similarity should be low. In the sense what? The distance between these 2 points must be high, right? When the distance between these 2 points is high, the similarity will be less. Is that right? So now similarity measure, as we are seeing here, the similarity measure is defined in terms of some Euclidean distance, right? So any doubts here? Any doubts? 1 minute, I'm going back. Any doubts here? When can I say 2 points belonging to two different clusters are similar? Yes, when can I say both are similar? If the distance between those 2 points is minimum. Is that right? Right? So in order to form groups, you have already seen this notion in k-means, right? That's why I told you the recursive partitioning of k-means leads to what is called as agglomerative clustering, right? In the agglomerative clustering, in the previous example, what happened? One point in one cluster, if it is in terms of distance, if it is nearer to the mean of other cluster, then automatically what happened? The point has shifted from the current cluster to the previous cluster, right? In the same lines, what is happening here? If you use single link clustering, what you are trying to say, that the distance between 2 points must be similar, must be minimum, right? Must be minimum. So that minimum is in terms of maximum. What we are saying is the in terms of what we are saying, the value of distance, right? The value that you see, right? So we will see with the help of an example, right? With the help of, yesterday I have shared you one link whose entire discussion is copyrighted. Now we will see that now, right? So in order to find this kind of clusters and dendrogram, how it is possible to do that, now we will see, right? Now see here, I would like to open that. So we have shared the link in the, during yesterday, I have showed a link. So this is clustering. We have hierarchical clustering, single linkage clustering, right? So you see, where is the next topic? Yes. Yes, this is single linkage clustering that now we are trying to understand. If this cluster needs to be combined with this cluster, then the notion of distance is in this way. the distance between this point and this point should be minimum. So in this dimension or in this direction, you look here to form clusters, right? Right. As we know, the intra-cluster similarity should be high, inter-cluster similarity should be low. Is that right? So it means in terms of distance, when I say that the distance is less, it is understood indirectly that these two set of points need to form a single group, right? These two set of points need to form a single group. Any doubts with respect to this point? Yes, participants, if you have any doubt, please let me know now. So if you have no doubts, I can continue. So in order to group these two clusters, we define this notion of minimum distance. So how this algorithm proceeds, right? I will show you. I think the screen is not visible to the participants. I forgot to share the screen. 1 minute. I will now share the screen. I'm sorry for that. 1 minute. Fine. I think the screen is now visible to the participants, right?
Yes, sir, visible.
Right. So that's what I'm saying. There are two clusters here. In order to combine these two clusters and to make it as a single cluster, the notion of distance should be minimum. When the distance between these 2 points is minimum, only then it is possible to merge and form a single cluster. Is that right? So that's why what we are saying is, in single linkage clustering, the word itself says you are trying to form a single cluster finally. So the notion says the distance should be minimum. So now how the algorithm proceeds? Now you see, first we should form a similarity matrix in this fashion. Now given the distance matrix based on the available data in this fashion. So how many points are there? Initially 6 points are there, right? We are considering 6 points and we are assuming that each points are individual clusters. Each points are individual clusters, and the distance between one cluster to the other cluster is shown in this matrix, right? You see the distance between A to A is 0. Obviously, all the diagonal values will be 0, right? The distance between A to B is 0.71. A to C is 5.66, right? If you see like this, you are seeing various distance values, right? Now, if you see carefully from this distance matrix, the least distance value is between the cluster D and cluster F, whose value is 0.50, right? Among all these values, the least value is 0.50. That is the distance between the clusters D and F. So what you should do? You should merge these two clusters first. The algorithm proceeds in this manner, right? You are merging these two clusters. And once you merge these two clusters, the point one need to understand is the earlier values will not change. Only the grouped clusters values need to update, right? Only the grouped cluster values need to update. Why? Because now you formed a new group, and now this group, the distance between this group with all the remaining clusters are to be identified, right? So that means these values should get updated. Now, how do you update these values? So this is the way you will update the values. Now, what is the distance between the group DF and A? So that you should do, right? So the distance between DF to A is formulated in this fashion. It is the minimum of distances between DA and FA, right? It is the minimum of the distances between DA and FA. What is the distance between D and A? Distance between D and A from the earlier matrix, distance between D and A is 3.61, right? What is the distance between F and A? 3.2. So substitute those values and you see what is the minimum value. Minimum value is 3.2, right? So now what you are doing, you are replacing this placeholder and this placeholder with the value 3.2 in the updated matrix. You see, you are replacing this value with 3.2, right? Now in the same lines, you are finding the distance between this DF cluster and other cluster B. So you are getting the values. Now how do how these values are obtained? These are obtained from the previous matrix, initial distance matrix, right? So from this initial distance matrix, you are considering the values and you are obtaining the newer distances from the merged cluster to all the remaining clusters. Now, after doing this, you should check for which particular clusters the value is less. From among all these values, the distance between A and B is less, 0.71. Now, what you are doing, you are now grouping the clusters A and B to form a single cluster. Now you see AB is now grouped, right? If you see carefully, the size of the matrix is getting reduced, right? Hierarchical clustering, in terms of matrix representation, right? What is actually happening? You are reducing the number of dimensions, right? Hierarchical clustering helps you to reduce the number of dimensions, right? This is with respect to mathematics, I am saying, right? So A, B, C, D, E, F, right? Now what you have done? Now you have grouped AB. Now once AB got grouped, these values are to be updated with the remaining clusters in terms of its distances. Now what is the distance between A, B and C? And what is the distance between A, B and DF? What is the distance between A, B and E are to be obtained here, right? So you are like this, what you are doing, you are simply updating these placeholders now with the calculated minimum distances, right? Now once you substitute these values, once again what you are doing, you are checking which particular distance for the in between two clusters is less, right? Now the distance between the clusters DF and E is less, right? DF and E is less, which is 1. Now what you are doing, you are now grouping DF and E together, DF and E together, and these calculations has led to the values, these values, right? Right, 2.5. The only calculated value is 2.5, which is obtained here. And among these values, which particular distance is less between the clusters? So DF comma E and C are to be now merged, right? So now what are the merged groups? DF comma E comma C and AB. Now till how much time this grouping continues? Until all these clusters form a single group, right? Like this, all these clusters should form a single group. Now in between these two, the least value is 2.5, right? 2.5. So then group these clusters, right? Group these clusters, and finally you obtain the value, minimum distance value to be 2.5 finally also, right? So if at all you want to calculate, you calculate, or else you no need to calculate, because it is the only value available. You can terminate the algorithm here itself, right? So finally what happened? You have grouped the uh, individual clusters to form new clusters, and these groupings are actually forming what is called as hierarchy in this fashion. Now what happened initially? You initially grouped two clusters DF at a distance 0.5. In the y-axis you have the distance value 0.5, and on the x-axis you have the individual clusters, right? So this grouping is in this fashion. DF and are grouped to form a single cluster till here at 0.5. And now next what you are doing, you are grouping A and B. You are grouping A and B to form a cluster at distance 0.71. And next what you are doing, you are grouping this DF with E at a distance what? 1. At a distance 1, you grouped, right? This is the new cluster now. You are now moved in up in the hierarchy, right? Now why you are moving up in the hierarchy? Because the distance is increasing. If you observe, this distance is increasing, right? This distance value, when you are increasing, obviously you are moving up in the hierarchy while forming the single cluster, right? Now what is the next one? At one you formed a group df and e. What is the next thing happened? Df and d is now merged with the cluster c at distance 1.41. Now the left out thing is this cluster with this cluster is to be grouped, that is grouped at distance 2.5. So this is nothing but the dendrogram representation of your clusters, agglomerative clusters, right? And this we have done with the help of single linkage clustering, right? The notion of single linkage clustering is the distance between the points in two different clusters should be minimum, right? Now in the form of let us say globular shape diagram. So initially you have merged two clusters D and F, then this D and F has merged, then AB has been merged, and the next thing is DF with E has merged, and this entire thing has merged with C. Right now this thing and this thing has been merged to form a single cluster. Any doubts with respect to this single linkage clustering? Yes, any doubts? So
Sir,
yes, please tell me.
sir, using the last graph, how we can say that DF is happened first and later AB is happened? Clustering.
Yes, this actually what we do is we know that in which order the clusters have been formed, right? The groups have been formed, right? So what we are doing is while plotting the globular shapes also, we follow the same order, right? So first we group D and F, then we group A and B,
Sir,
because yes,
just
yes,
by seeing the graph, how I can say, sir, by using dendrograph, I can say, dendrogram, I can say that first DF is happening, later AB is clustering.
yes,
By seeing the last graph, how I can say that first DF
yes.
is clustered and then AB has clustered.
The way to sequentialize which cluster has formed first is to label that cluster to group. You specify the sequence number. It is possible to associate a label for each cluster, right? So you might have a surprise here. How a label can be assigned, right? A label could be a sequence number, as you are seeing here. A sequence number can be associated with this, right? So when a sequence number is associated with a cluster, obviously when you visualize with the sequence numbers, the groups, obviously one will understand that this is the
That,
first group cluster and this is
okay,
second group
understood, sir.
cluster.
Understood, sir. Here sequence number is missing now, I think.
You can associate. Actually,
Ah,
we never show you the sequence number.
okay, sir.
But in as I told you earlier, there is a tool called Veka. If you associate in Veka, there is an option to add label information to the cluster. If you add label information to the cluster, it is very much clear that these set of examples belong to that particular category, right? So that is possible. Now what you are doing when you associate label to the cluster, you are moving away from clustering process and you are saying that you have formed categories, right? In the same lines here, we are not saying that we have formed categories. Instead of that, we want to know whether which cluster has formed first, so we are associating with the sequence number.
Thank you, sir. Thank you, sir.
Okay, sir. Okay, thank you. Yes, any doubts further? So now what I do is I will once again come back to the presentation. Where is the presentation? I think it is here itself. 1 minute. I will. Yeah. Right, now we are back to the presentation. So this is a single link way of agglomerating or grouping the
Sir,
points.
make it in the presentation notes. Sir.
Yes, yes, yes. So, fine, sir. Thank you. Right. This is the agglomerative single linkage based agglomerative clustering, right? And you see these are actually forming what are called as hierarchies, right? Now there is another way to do this clustering. The second way of doing the clustering is complete link clustering. This complete link clustering acts in the opposite way when you compare with the single link clustering. So in single link clustering, what we have done is we said the points in between two clusters, the distance between the points in between two clusters should be minimum, right? But in complete link clustering, the distance between the points in the two clusters should be maximum in order to group, right? So this minimum in the sense, the similarity should be minimum. That's what the notation. That's what is your similarity measure? What is your similarity measure? You are saying you are using some Euclidean distance or something, or it could be a cosine similarity with respect to documents. So what is your similarity measure that you use? Accordingly, you are applying minimum function to say that the points between the in between the clusters, right? The distance between the points between the clusters, right, in terms of similarity should be minimum, right? So this is the way the clusters will form in complete link clustering, right? So of course we are not dealing with this, just to make you understand I'm showing you here, right? Then now coming to the scenario, coming back to the scenario, to know about the component similarity analysis in product design in to form clusters, right? The data is plotted in this manner, right? Now what we are doing is we are using this hierarchical clustering to form the dendrogram, right? How many here this diagram or this particular representation of dendrogram uh, shows you uh, there are some different number of clusters here, right? Because we haven't I haven't used single linkage clustering to form this dendrogram. Dendrograms can be formed with different types of clustering techniques, as you have seen: single link, complete link, right? You have altogether Ward is a person, is a computer scientist who has defined his own way of forming dendrograms. So Ward way of forming dendrograms is also possible. So what we do is, in while we are doing lab sessions in the afternoon, we will simply modify the mode of forming dendrograms, and we will see how many clusters are actually formed, right? So if I select the value Ward, then how many clusters are actually forming? If I specify the value to be single, how many clusters are actually forming? We should see, when I specify the value to be single, the number of clusters formed finally will be only one, right? So that we will see while we are doing lab in the afternoon session, right? Now, as you see from these scenarios, the number of attributes are actually high, right? The number of attributes, these are nothing but dimensions. So when the number of dimensions are actually high, it is computationally complex. After certain number of dimensions, the algorithm as well as the way the computation happens, due to the limitations with respect to the processing capabilities of the programming language, right? It is not possible to go beyond those many number of attributes and analyze to form groupings. So at that point of time, what we say is we are what is say encountered with the problem of dimensionality, high dimensionality, right? So when that is the case, your distance measures, when and you encounter high dimensionality, your distance measures and similarity measures will become meaningless, right? So how do you then approach to this problem? How do you deal with this problem, and how do you handle this situation is actually to be understood now, right? So high dimensional spaces will increase the risk of providing overfitted clusters, right? So the clusters seem to be perfect while we perform clustering. Once we evaluate the goodness of a cluster, it will become poor, right? So that is nothing but overfitted cluster, right? So we should come to a consensus to say that we are able to handle high dimensions, and we are able to form clusters. And when we are handling high dimensions and forming the clusters, right? When we are handling high dimensions and forming the clusters, 1 minute, why it is showing like this? Fine. Clusters, we are able to reconstruct original data out of the reduced number of dimensions. That is the essence of dimensionality reduction. So if you are reducing the number of dimensions by using certain approach, that reduced dimensions should be in a position to reconstruct the original data, right? That is the essence of dimensional reduction, which is possible through the technique called principal components analysis, PCA, right? So we are going to see that PCA now, right? So you see this image carefully. If there is one-dimensional data, you can plot it on a simple straight line, right? If you have two-dimensional data, you are plotting on two axes, x comma y. If you have three-dimensional data, you are using the third dimension to plot and to analyze the data. But what is the case when you are moving away from three dimensions in the representation itself, right? Forget about the programming way. What is the fourth way? When you when you add that fourth dimension, how do you represent the data, right? So the cubic nature is present for three dimensions. For fourth dimension, what is the way to plot the data? How do you show, right? That is one important point. And next is when the number of cells will grow exponentially with when you increase the number of dimensions, right? If you say that I would visualize my data in terms of cells, in terms of squares itself, by increasing the number of dimensions also, it means you are using the cell representation, but these number of cells will grow exponentially, right? Enormously when you are increasing the number of dimensions. Obviously, which particular set of points are actually useful to form good clusters is impossible to know, because in this kind of representation of high dimensional data, what happens is the notion of similarity or distance measures is not appropriate to deal with, because which particular point is nearer to which other point is not possible to understand, right? That is the way, that is the problem with high dimensions. And this problem is technically known as curse of dimensionality, right? So to deal with this curse of dimensionality problem, what we are doing is we are approaching with a mathematical technique uh, known as PCA. There are so many techniques to handle high dimensional data. We are seeing only one technique, that is PCA. Now, what is this PCA? So before talking about this PCA, as I told you, what is the connection between dimensionality and clustering? So you see, uh, this is what the notion of distance become meaningless, and it is not possible to form groups from the high dimensional data, right? And obviously there is another problem called sparsity. What happens is certain dimensions will hold very few non-zeros, so at that point of time, the if you cannot cannot clearly use the distance measures to form groups in high dimensional spaces too, right? So these techniques these problems are to be handled. So what we are doing is we are saying that we are reducing the dimensions by using the technique called dimensionality reduction. So this dimensional reduction, what it does is it will reduce the number of attributes to some k number of attributes. If there are n dimensions or n attributes, it reduces to k dimensions, And what it says is it preserves the essential information. This is the interesting point while you are reducing the number of dimensions, right? So the when you are reducing the dimensions, the information should not be lost. You should preserve the information, and that too, essential information is to be preserved. So in image processing techniques, right, in image compression techniques, actually this dimensional reduction is useful, right, in general, right? Now the primary goal is to simplify the data set and make it computationally efficient. As I told you, working with high dimensional data is computationally expensive. To make it computationally efficient, what we are doing is we are approaching to dimensional reduction. The technique, the approach, consider the mathematical approach that we are using here is PCA, right? What is this PCA? PCA is a technique that transforms variables into a new set of variables called principal components, right? So how the variables, existing number of variables, get transformed to new set of variables, we will see in terms of steps in the next slide, right? So now once these are converted to new variables called principal components, these principal components, when we are transforming, these transformation steps will be in such a way that the original data is in the form of linear combination, right? Is in the form of a linear way, linear combination of original variables. And these principal components, if you plot in the vector space, these will be orthogonal, right? One principal component will be perpendicular to the other principal component. So that is the important point, right? Now let us say we have formed for some time, we assume that we have obtained two principal components, and when you plot those two principal components, as I told you, those will be perpendicular in nature, right? And at any point in time, the first principal component accounts for most of the possible variation of the original data. So whatever variation that is present in the data, that most percentage of that variation is captured with first principal component. So if that is the case, then it is easy to reconstruct the original data from this principal component. Is that right? Because original data itself possesses diversity and variation in actual sense, with high dimensions. If most of the thing is captured by first principal component, then we can easily get back the original data. Then the second principal component also tries to capture variance in the data, but not as high as with the first principal component, right? So how this looks like, what are the steps that we use to form principal components? So we will see those steps now. Now the first step is we will collect the data, right? Collect the problem relevant data, we'll collect the data, and then the next step is we'll calculate mean for the data, right? Mean for the data. And step 3 is we'll find out the difference between each and every point in the data with the mean, right? We calculate that difference, so that what happens, the points that are plotted initially and that are shown in one particular quadrant will now move away from the mean, and we say that the points are now varied. That is, when the points are away from the mean, we say that they have certain variation, right? So once the points will move away from the mean, what we do is we construct a covariance matrix on that step 3 data, and to form which particular set of points are highly related, highly dependent, right? And so now, are highly independent, let us say. So once you form a covariance matrix, it is possible to draw eigenvectors and eigenvalues from that covariance matrix. So there are techniques to obtain eigenvectors and eigenvalues Gram-Schmidt orthonormalization technique is one such technique we will use to generate eigenvectors and eigenvalues from the covariance matrix. So once these eigenvectors and eigenvalues are obtained, based on the obtained eigenvalues, we choose the eigenvectors as principal components. Right? These eigenvectors will hold the original set of data in the form of linear fashion. So once we get eigenvectors and eigenvalues, we sort these eigenvectors or eigenvalues in the decreasing order. So when we sort these eigenvalues in the decreasing order, the corresponding eigenvectors can be identified, in which the first eigenvector has the corresponding eigenvalue to be high, and the second eigenvector has a somewhat less eigenvalue as compared with the first eigenvalue, and so on. When you have an empirical threshold, now based on that empirical threshold, you can say that after a certain eigenvalue, you ignore the remaining eigenvectors, right? And you say that those eigenvectors are not required for me to capture the entire variability of the original data and preserve the meaning of that actual data, right? So that is your step 6. Whatever I have now discussed is nothing but your step 6, and choosing those components and forming and saying that those are the final number of principal components, and you can what you say, with the help of that principal components, you can derive a new data set also, right? So by using certain what is the inverse steps, as we are this entire process we work out with the help of matrix notation, and we use matrix properties, matrices, the properties of matrices to what you say, derive these new sets and new data sets and new components. And when we do inverse of this process, we can actually get back the original data, right? So any doubts with respect to this discussion? So representation is possible in many ways, but the real challenge is about visualization. True, sir. As you said, rightly said, you can represent the data in many possible ways. But the important thing is the way the structure the structure of the data is present. Based on that, we need to move ahead, right? So then, so this is uh, a generic representation. How do you reduce from high dimensions to low dimensions, right? From 2 dimensions, this is a 2-dimensional data. You are forming a new component called principal component, and you are saying that this is the final dimension, right? This is your 1-dimensional data. Now you have now reduced from 2 dimensions to 1 dimension. Now in the same lines, your 3-dimensional data has now got reduced to 2 dimensions because of 2 principal components, right? So now in this transformed space, you are plotting the transformed data, right? This transformed data is actually preserving the, and these transformed data and these transformed vectors are actually preserving the entire data. So that's why it is possible to reconstruct, right? Now, so once again, I'm taking the same quality control scenario in manufacturing, and I'm using a PCA here to form the principal components from the data. And we have seen 2 principal components obtained from the data, right? These 2 are enough to explain entire variation present in the data set. So that's why what I'm doing is I'm using these 2 principal components. I'm deriving a new data set and plotting here, right? So any doubts with respect to this? Participants, if you have any doubts, you can type it in the chat box, or you can unmute yourself and ask the question. So with this, we have come to the end of the end of the discussion about unsupervised learning, right? Today in the afternoon session, we start from 2 p.m. and we first deal with a simple represent a simple way of forming clusters by using k-means, right? And then we will go through the actual scenarios, and also we will quickly show how we will find out the component similarity with the help of two different gears, right? Two spur gears, and what to say, there is another kind of gear, like similar gear, which is helical gear, right? So with the help of what you say, similarity measure technique, and we'll compare the images, gear images, and we'll come to a conclusion also. That thing also we will see in the afternoon lab session. Right. Is it that? Thank you. That is helical gear, correct? Okay. So with this, we come to an end of this session. So I will stop sharing now. Sir, shall I leave the session? If participants have no doubt,
yes, sir, I'm ending the session.
if the participants have no doubts, then I will leave the session.
Thank you, sir.
Thank you.
Thanks.
Okay. We'll again meet at 2 p.m.
Okay, thank you, sir.
Fine.